Hello everyone, this is Space Café Podcast and I am Markus. "2024 will be a wild year in space exploration. We're looking at continued Mars exploration, humans returning to the moon, SpaceX Starship tests, and potentially the completion of the Chinese space station Tiangong. And get this, we will witness in operation one of the most spectacular missions in recent times, ESA's Euclid mission, aimed at surveying the dark universe to unravel the age-old question, why is the universe expanding faster the further out we go? And where is all this mass hidden that we can't see and that we're surrounded by? So, where is all this happening? Euclid has made its way to this famous spot in space called the L2 point, about 1.5 million kilometers from Earth. It's super stable, perfect for some serious space gazing. And it's not just hanging out there alone, it's right near the James Webb Space Telescope. But here's the twist. Euclid is playing a different game. While James Webb Space Telescope gives us these stunning snapshots of the cosmos, Euclid is on a galaxy hunt across various distances. We're talking about a journey back in time over 10 billion years. Now, what's at stake here? It's all about unraveling the secrets of dark matter and dark energy, this mysterious forces delivered to be the driving force behind the universe's accelerating expansion. It's detective work on a cosmic scale. If Euclid delivers, we could finally get answers to questions that have puzzled us since Edwin Hubble's groundbreaking observation. Galaxies far away seem to be rushing away from us faster than we ever thought possible. Mind-boggling, right? Well, to me at least. And today, folks, we've got a real treat for you. We're sitting down with Giuseppe Racca, the driving force behind the Euclid mission. And he's here ready to shed light on what the mission could mean for us Earthlings and give us the scoop on the current state of astrophysics. So strap in and get ready for a conversation that's bound to be out of this world, as you'd expect from the Space Café podcast, right? Ladies and gentlemen, it's an absolute pleasure to welcome Giuseppe Racca to the show.
You're welcome.
You've been here quite a while now. How many years now?
I've been here for 36 years in ESTEC.
That's crazy.
Nearly more than half of my life.
How's that feel for an Italian here in the Netherlands?
Not too bad, because actually I'm from the north of Italy, and at the time, 36 years ago, we had very bad winters in Italy, in the north of Italy, and there was actually the winters here were even milder, so then it was not a problem. It was more a problem the summers, that you never have a real summer in Holland. But now everything is changing with this climate change, so now is the perfect time of the year in Holland is actually in the summer, because the summer is always very nice. No, it has never been a problem for adapting for weather or cultural. In ESTEC, we are international, so we are from all European countries, and this is really what I liked. So then I like to work in an international environment. Holland in general is very international, and so it was good.
Why are there so many Italians around this place? I mean, like wherever I go, I would hear Italian language. Is there a specific affiliation by Italian people for the space industry, maybe?
That's a good question. I think many people realize that there seems to be a larger share of Italians than what ought to be, let's say, in terms of how much the population big is or how much the investment. Okay, first, Italy has quite a large investment in space, and in ESA is actually the part of the big four. Let's say this Germany, France, UK, and Italy are the biggest investors in space. And the UK and Italy, it depends. I'm not so sure about what is at this very moment, but they are typically, let's say, Germany and France are a higher investor, but UK and Italy are nearly the same. So this, of course, gives a good share of people who are actually directly involved with the investment. And then, of course, in terms of research scientists, and I noticed that as well, that also in Holland, there are many people coming from Italy, connected to space or not, but at least connected to science. And they work, for example, University of Leiden. There are so many Italian researchers, professors, that it's possibly is due to the fact that the research condition, economic condition in Italy are worse than many other areas in Europe. And okay, I know about Holland, but I'm sure it's the same also in many other areas. In Italy, unfortunately, let's say there is an export of intellectual workers, let's say.
I get the impression that there's a different appreciation in Italy for the natural sciences, maybe also in the educational system already. So maybe the school system and universities are more targeting natural sciences in Italy, maybe. But you're the expert.
But I'm not really the expert because I'm away from Italy for a very long time. I believe that natural sciences are very important in Italy, and people like it. But I think it is more due to the fact of lack of opportunities in Italy, or let's say less opportunities in Italy than abroad. What I find, for example, is especially in the academic. You have the way that the researchers and professors progress in their career is more difficult and in many cases less transparent than what you have abroad. For example, it happened to me that just very recently I met a very, very young researcher in cosmology, and she finished her PhD, or she was mid of her PhD, and then she wanted to try a postdoc position, and she had really troubles to find something in Italy. Instead, he found something immediately in Stockholm. So then she moved there. I believe it's easier to find a good position in science in abroad than in Italy. And one other thing that I also believe it is still true, I don't know for how long it will hold, is that the education, let's say the science education in Italy is pretty good. So then I also, when I do interviews myself, I always find that the university preparation for in terms of scientific background more than in terms of practical application is very good.
Let's move to your favorite subject, and that's right on display, right behind you, the Euclid mission, a fascinating mission that also taps into maybe one of your personal passions, the discovery or a solution to a cosmic embarrassment that we are as humans under, because we have no clue what is going on in our universe. So is the cosmic embarrassment, would that be a term that you coined?
Sure. I think I used that cosmic embarrassment many times, in fact. But for me, it has been really a big drive for my career. I was at the time, at the end of the 90s, I was actually working in planetary missions. So then I was taking care of studies of planetary missions, which some of them, they were actually realized, some other not. But I remember when, at the end of the 90s, there were two very important discoveries made in cosmology. Let's say one is the fact that the universe is flat, let's say spatially flat, and the other one is the accelerated expansion of the universe from the supernovas. These two new ingredients, really constrained a lot the cosmological models, because before there were many more freedom still there was still the possibility that the universe was actually not flat, and therefore there was some curvature. The curvature also contributes in terms, it's a little bit like matter in the Einstein equations, that you can still contribute in making the overall budget of what there is in the universe becoming true, even without dark energy. But now, then when this was discovered, the flat universe and acceleration of the expansion of the universe, then there was no other ways than making an hypothesis of dark energy. Dark matter was already there because of other reasons, but just counting up in the budget, it made up 95%. Mm-hmm. And that was really terrible. And I remember at the time, I was really just guessing. I said, we should really have a mission, a dark energy mission. Let's say discovering dark energy at the end of the 90s. Okay, I didn't know even what I was talking about, obviously, but then the scientists made some clever ideas of how this actually dark energy could be measured, could be investigated further. And then after many years, there were many proposals for studying dark energy and dark matter. And one of them that became, in the end, Euclid, actually two of them, which were merged and then became Euclid. And in the meantime, I did many other things because my job was not this one. It was more my passion than my job. But and then when it was, I was working on a mission for preparation for technology for gravitational waves detection, which is LISA, that is starting now. And at the time, then Euclid instead was approved. And then when it is approved, it is necessary in the ESA system to have a person appointed that is the responsible for the mission. Responsible for all aspects, although, of course, you cannot know everything, obviously, but you need to be able to coordinate and to be responsible for the all aspects. And then I was asked to take this up, and I did it.
Does this embarrassment and this challenge that we are not knowing what is going on around us only apply to cosmic dimensions, or would that also apply to, like, right now where we are sitting right now, not on the microscopic, on the quantum level, but also in the macroscopic level that we're experiencing now?
You mean if dark energy and dark matter would have an influence in our macroscopic world? Or
maybe not only an influence, but like we're sitting right across one another right now. So 4%, so is this the 4% that we're understanding? Could 96% of what we're being surrounded right now be something that we do not see, we do not sense, we do not understand right here, right now?
Yeah, actually not. Because what we are here, let's say the density of matter and energy of us, here we call us, the cosmologists call this baryonic matter, but anyway, this matter, this density is incredibly high. Let's say we are made with a density about the water density, let's say 1 tons per cubic meter, and anything else is slightly higher than that, the computer is a bit higher than that, etc. So if we count the density in terms of protons per cubic meters, we are talking about here, I think, if I remember well, 10 to the 27. So then it's very high density. Despite the dark energy, which has occupy 95%, dark energy and dark matter that occupy 95% of the whole universe, it's only 6 protons per cubic meters. So then it is true, between us here, we have dark energy and dark matter, but the average density of that, supposedly that dark energy is spread around evenly, which it seems to be, it would be still only a tiny, tiny fraction of the very high concentration of baryonic matter that we represent. So in our environment, you can never detect anything like that. That's why also Euclid is difficult mission, because you need to be able to detect a signature of something which is very, very important at cosmic level, absolutely important, 95%, on very high density areas like galaxies, like any baryonic matter, which in itself has an incredibly high density of non-dark energy. Therefore, the signature of that dark part is very difficult to detect.
Fascinating. So how does one approach such a problem from an engineering level, from a scientific level? How did you, for the first time, when you said, hey, we could use such a mission, such an instrument, how would you approach people for the first time? And how would they react to it?
First of all, let's say what we have, when the Euclid mission was created, it was based on what we call probes, let's say techniques of how to make measurements about dark energy and dark matter. And these techniques were actually techniques developed through the years by many scientists who had the idea to, let's say, for example, for dark matter, let's see how the galaxies, the faraway galaxies change their shape, and the shape is changed due to the fact that we see it deformed by weak gravitational lensing from the light that goes through the matter, both dark and visible. And then since the visible, you see it, you remove it, and what you have left is the dark matter. So this is an idea of how you can measure this dark matter distribution. Then in practice, and here it comes the engineering aspect, then you have to say, okay, fair enough, but am I able to build an instrument, a telescope and an instrument that is able and is accurate enough to measure this very small distortion? And to do that, it's a very lengthy process, and this is actually what we started in our work. And at the beginning, it's not clear at all that this can be done. But then you break it down to various aspects, and you see little by little that you can actually achieve that if you can build such a telescope with such a precision, such wide angle, such image quality, etc., etc., etc. And what is interesting in Euclid is that we have never been really sure that we could do it. Let's say because it's really at the very extreme of technology, whether you can achieve that. It's basically a perfect telescope. Let's say we have very good telescopes already on orbit and on ground, but this one has to be perfect, because if it is not perfect, you cannot really achieve this performance.
What does perfect mean? Because now the James Webb is supposedly one of our greatest telescopes ever, but what does perfect mean?
But perfect means in optical, for example, optically, they call it diffraction limiting. Let's say light has two forms: is wavelength and also let's say particle form. But concerning its wavelength aspect, it has what is called diffraction. It's an effect, and this all this diffraction makes so that you would, if you watch a point in the distance, the point will never be only a point, but it will be a point with a certain diffraction pattern. But typically, this is not a problem for ground telescope or for other, because the problems we have, for example, from ground telescope with the atmosphere in between is so much larger. All the molecular of the air is so much more distorting than this limiting of the diffraction itself. Instead, in space, we can do that, but of course, to do that, you need to build absolutely perfect optical surfaces. And a perfect optical surface, for example, typically on normal telescopes, the optical surfaces are spherical, but these spherical are actually giving aberrations which do not let you reach this level of diffraction limiting, because you have other aberrations. So you have to basically remove all possible aberrations. So you need to design a perfect telescope without aberrations. It's like a theoretical telescope. Let's say you need to realize in practice something which is true only on paper, but you have to realize.
So who would you approach for a job like that? Who would you call? I mean, like, I guess there are companies out there who would build telescopes, but this is not an off-the-shelf telescope.
Not at all.
So would the technology to build something like this need to be invented at the same time?
Yeah, let's say we based it, in fact, at the very beginning, we had in mind two type of technologies and which were existing. One is actually proprietary of Airbus in Toulouse, and the company called ESTEC, who is a company who produces optical elements for many, also for ground and also for other applications. And these are made of silicon carbide. Silicon carbide is it's a ceramic. It's the way of constructing is like a ceramic, but it has a very good properties that is conducting heat a lot and is deforming very little, nearly nothing. So then by these two aspects are very crucial, because conducting heat, it means that you have everything is at uniform temperature, and not deforming is not making any change into the optical path and to the length, shape, etc. We also had another technology, and so we actually put in competition these two companies who could produce that. We made a bid, let's say, and then we finally selected the one that we thought it was more promising, and it was this one that I'm describing, the silicon carbide. However, making everything in silicon carbide has also a lot of drawbacks, because ceramic, mind you, you have to build a car all in ceramic. Mm-hmm. So that would mean that you have to design all possible parts, and then you start building them, and then you cannot repair anything, because ceramic, you cannot touch it. Let's say you can glue it, or there are some process of gluing it, but that's it. You cannot drill a hole. So then if you have forgotten to make a hole in one part, you have to redesign it all, or you wait for ages before you start manufacturing it. And then when you manufacture it, you discover that a part you cannot make. And then what do? You restart the design and then changes other things. So it has a lot of drawbacks. It's not something that otherwise everyone would say, okay, let's use it. Instead, however, we made it. So we had some delays, in fact, due to this reason. I think a couple of years of delay, just because of the fact that the readiness to manufacture with all the details took much longer than what we expected. But I am pretty sure that we did the right choice, because now I'm looking at every day at the data coming from the satellite, and we see how crucial is this aspect of thermal distribution, evenness of thermal, to obtain the optical quality that we need. And I would really doubt that without this technology, we could achieve what we have achieved, what we are achieving now, because we are not.
That's so fascinating, because you could also say this is an intentional invention. So that something needs to be invented, and there is no failing possible. So because you need to have something delivered, because otherwise the whole mission will fall apart. So that must put quite a bit of pressure on all the involved parties. Is there an option that a theoretical concept can also fail and not be able to be invented, be developed?
Yes. I think it is certainly in these most advanced missions like this one. For example, I can take, just deviating a little bit from Euclid, in my previous mission, ESA Pathfinder, we were asked to measure gravitational waves. Actually, we were not measuring gravitational waves, but we were testing the technique to measure gravitational waves. And the measurement that you have to do there, it's really much less than the size of an atom. And you need to make that measurements while anything in the normal life changes shapes and distances for much, much more than that. So then how could you be able to measure something so small? And you have to basically to do it in practice, and in this particular case, there were, let's say, special forces inside which normally one neglect because they are not affecting the microscopic world. Let's say special forces between atoms and between objects which you typically disregard completely. Or, I remember the time we were talking about outgassing of metals. Also, there is some gas trapped in a metal, but you normally don't really look at that because it's not an important factor. Instead, there it was important. So in that particular mission, for example, we were really doubting until the end whether we could actually do it. And also we had technologies, ancillary technologies, which I'm not going to spend too much time to talk about, but which we developed at the same time, and we failed as well. And we failed, and we had to go to other technologies. In the end, for example, ESA Pathfinder worked pretty well, and actually we achieved better performance, much better performance than what we thought. And when I do my lectures about this, I typically ask people is this a good result or not? Let's say, because we achieved really nearly one order of magnitude better than what we were supposed to achieve. So one could say, yes, it's good from one side, but it's bad because you spend too much money, too much time, etc., to achieve something that you did not need. But this comes from exactly from what you were asking before, let's say, because we were not sure whether we would actually fail or not. So then you try, and then your results may be a failure or may be overshooting into the performance.
My audience knows that I'm always looking for inspiration from science, from big science, for civil society, because I have the impression that the problem-solving capabilities and capacities in science is something we could draw inspiration from for our civil social problems, not least for climate change issues, for all those issues societies around the globe are being confronted with. So what is it that you do differently in big science? Because I feel like failure is almost not an option. And usually, next to impossible things like James Webb, like Euclid, like LISA, they work at the end. How is that and why is that?
Yeah, I think it's a very interesting question, this one. In fact, I ask myself the same. I think, in a way, in this fundamental science, our job is easier than in society because we have a very precise question, and what you want to actually solve, it's a difficult thing, but it's precise and understood, and it's unique. Instead, I see that in society, in many cases, most of the cases, this is not the case. Let's say you have maybe a big problem that comes up that you have to solve. But it's not the only problem. First of all, you don't understand it completely. And then it's not even the only thing that you want to solve, because at the same time, you also want to solve another problem. For example, you mentioned climate. I remember I studied nuclear physics and engineering. So then I was really very much into the nuclear aspect of also concerning the nuclear energy, etc. And I remember at the time, already many years ago, because it was not yet well known to the society that carbon dioxide would have brought to these climate changes, but it was known already in my studies 40 years ago. That was known. And so then it was said, okay, this is the problem. Nuclear energy is definitely the best way of solving it because it does not emit CO2. And so why don't we go for it? It seems so simple. Let's say from a purely scientific point of view, this is a simple question. Nuclear energy were established. Of course, improvement were still necessary, etc. But it was very well established. But why instead it was decided to do just the opposite? It's because the problem was not only the climate change, the CO2 emission. First, because at the time was not well understood yet. Let's say it was understood, but not. It has become really public knowledge only in the last probably 20 years or maybe even less. And second is because that was not the only problem, because another problem was also the fear that people have about nuclear energy. So then solving this problem in terms of climate, let's say, avoiding the problem of the climate change, it was a very difficult one because it was not unique, it was not well understood and not unique. And I believe in that sense, many other problems in society are difficult. I still believe that if one would take a scientific approach and really be able to identify what am I going to solve now, we would be better than what we are doing now in society in many aspects. But I also recognize that let's say the sociological, the social issues have so faceted that it's difficult to isolate. It's diffused.
Yeah. We won't solve our social problems here at the table. So let's go back to Euclid. Euclid is up and running. So how was the launch? Did everything run smoothly?
Yeah, the launch was fantastic. Let's say we had, we were supposed to launch with Soyuz, but then after the aggression of Russia to Ukraine, we couldn't work with cooperation with Russia. So then we had to change, and changing launches so late it's really a big problem. And fortunately, we had this opportunity to go with SpaceX, and it turned out to be a fantastic experience. Let's say SpaceX is a very different company to any other companies we have in Europe.
How far is it different to work with?
Very different.
Is it like taking a bus?
It's a little bit like taking a bus. And but just to give you an example, at the same time I was in Florida with the launcher from Cape Canaveral. My colleagues in JUICE, they were in Kourou for launching with the last Ariane 5. And they were there alone for 5 or 6 months before, and they would have been the only one for another 5 or 6 months after their launch. When I arrived in Cape Canaveral, we were number 42 to be launched, something like that. So then when you ask a question, you say, sorry, I would like to check it. Okay, when it comes your turn, you will talk. So this was the type of feeling we had. Of course, they were not treating us badly because we were a European customer and a very important mission. Let's say our mission is more than $1 billion. It cost much, much more than many of their launchers. So then they had not to, let's say there was no jokes to be made and no cutting corners, of course. They were appreciating that. But the environment was a little bit like that. For example, I remember in other missions, you go to the launch tower many times to see it, to visit it, etc. Then just to see it as well. And in this case, I went to the launch tower 6 months before launch and never again. So then, because it was always occupied by someone else. Yeah, or because of they also have a lot of military restrictions, etc. in Cape Canaveral. But in practice, it is very different. But one thing I must say is that they are all very young. All the people I met in SpaceX, I used to say that nobody's older than my children there. But they are really young and good, and they are empowered very much by, I think Elon Musk himself has that style, let's say, empowering people into, let's say, people who do the job, who know to do the job. They are the people who decide, even if they are 25. I mean, it's and that's it's a powerful thing.
How can we stay competitive in relation to that now with Ariane 6 coming up? Do we have a realistic future with these competitors?
It's a very difficult question
I know it's difficult
to answer, but I would say that the competence in Europe is there for sure. The attitude is different. And I think it's not so different from what I said before about the society. Let's say that SpaceX, Elon Musk in particular, he had an idea. He wanted to go to Mars. He wanted to build a launcher, a vision. Yeah. And he did it because he has the power to do it. Let's say he put some of his own money, but not only, because he also got a lot of money from the government. So like we all do. So in that sense, it's not that different. People believe that Elon Musk did everything with his own money, but that's not the case. I mean, but he had this decision power and the vision and the freedom to do everything he wanted. Again, if we translate that into Europe, our situation is very different. We are made of many countries, and we have our decision makers. They are European, ESA, European Union, and the countries themselves. So it is very difficult that someone can take a lead and decide and do everything he wants. It would be impossible. And at certain point, to do something really bold like this, you really need to be one man who can really decide and do the things. And I find this very difficult in Europe. This does not mean that we cannot do great things. And I'm pretty sure with Ariane 6 now restarting, hopefully, we will also do great things. But the situation is very different.
Good. Back to the launch tower and the launch date. So you're closing in. You have your slot, your schedule, the next bus coming up. And with Euclid as the cargo, how was that?
Yeah, it was actually, we managed in the end to have nearly 1 week, I think, of free time for us, let's say, before the last bus went. So everything is very, very tight in the schedule. Let's say all things you have to do, the transportation of the various stages of the launcher, the installation of the Space Café into the launcher, etc. All these things are all very compressed, all these phases. And then we arrived the night. We were supposed to launch in the morning at 12. No, so I forgot when it was in the morning, but it was in the morning to launch. And then we were going on duty at around midnight. Let's say around midnight, we were going to the launch pad and then to the mission control center. And when we arrived at the mission control center, actually we discovered that there was a problem on the launch pad. And the problem was on the launch pad. It was nothing to do with the launcher itself, but it was a big problem on the launch pad. So something that it would have been nearly deciding to postpone the launch. But talking to SpaceX, they said, okay, I think we can fix this problem. We have called the engineers and everyone needed to fix the problem, and we can still do, and we are not giving up. And I was thinking that giving up yet, but maybe we will give up. But instead, we're not giving up, and we didn't give up. And the launch took place. Let's say all this had to be fixed, and it was fixed. It took us a couple of hours, but we recovered that in the later sequence of the various tests that you have to do once you are on the launch pad. And then the launch took place at exactly the time that it was supposed to, the 1st of July, like we predicted 1 year before. And the launch was perfect. We had also, for our particular mission to go to L2, the launcher had to follow a certain trajectory that they never did before. So then we had to install the ground station in Brazil, for example. And then there were a number of maneuvers also from the launcher, which were not standard. But everything worked perfectly. They released us exactly in the correct trajectory. So correct that we did not basically need to make any correction maneuver. So then we saved actually 43 kilograms of hydrazine.
I've always asked myself, what if something happens, an anomaly during the launch process, and you lose your spacecraft? Is that the end of the mission altogether, or would you be able to rebuild or have a spare spacecraft somewhere sitting around? Or is this the end of 20 years' work?
I think in practice, except few cases, I think in practice, okay, we have few cases. Let's say cluster 2 was rebuilt. Also the Arctic, I forgot the name, Earth observation Arctic spacecraft was also rebuilt. But typically it is the end. And I would expect that for something like Euclid, that it took so long to build. Even if we have a lot of spare parts, we even have a kind of nearly complete telescope that we could be reused. But it would be very difficult in practice to rebuild the mission. So the disappointment, to say the least, of a launch failure is really terrible, because it's really wiping out 15 years of work and with very little chances that this can be redone. Also because the science goes on. So then probably if you would have to restart now and to launch in another 10 years' time, you would need to do something different because in the meantime, you know that there are WFIRST, there are other satellites that will be launched by NASA, for example, in a couple of years. It's not in 26, probably. It's not exactly the same like Euclid. It does slightly different things, but you would then need to take that into account, that there will be another one already operating. There are also other missions from ground. Let's say there is an observatory, LSST, from ground, who is also start observing, I think, from mid of next year. Also, you would need to take that into account. So then it would be very difficult to just rebuild Euclid. I'm pretty sure we would have rebuilt a dark energy mission.
But
not Euclid.
Are such missions insured by insurance companies? Who would take the risk?
Typically not. Typically we don't insure because I remember in the past, in one of my past missions, I had inquired with the insurance company if it was possible to take it, but the insurance premium is so high because the risk is high, and therefore we would never have the budget for that, and the budget for that would need to be approved by the member states. It is not in my budget. So when I start a mission and I have the budget delegated, I don't have a part. I'm not allowed to take an insurance. But I'm not excluding it. I think in the future, for example, in fact, with something like Falcon 9 that never fails like that, probably also the insurance premium would really go down. And maybe if it turns out to be that you have to pay maybe 1 million, then maybe it can be done. But at the moment, it's still tens of millions. So then that's a big money.
So Euclid is up and running, has reached its destination. You get the first data set. How was that?
Yeah, the first data set, we a little bit wanted to have it really to show for communication purposes, to show what Euclid could do, but also to show what that we can actually achieve the performance that we were all expecting, that the mission demands. Euclid, in practice, what we'll have to do, it's a kind of statistical mission. So it will make many measurements, but it will not produce, let's say it can produce very pretty pictures, but it's not the purpose producing pretty pictures, but it's to make measurements of these tiny galaxies that you can barely see. And we make
Isn't it the optical spectrum?
Both optical and near infrared.
Okay.
So we start from 550 nanometers to 2 microns. So it's covering... but we said, okay, let's use this. Let's make some observations of objects, both inside our own galaxies, which we completely disregard our own galaxy because we want to observe very distant things. But let's observe our own galaxy, and we have made these two observations: the Horsehead Nebula and also a cluster, star cluster in the galaxy, globular cluster. And also made progressively far away distant objects observation, including the Perseus cluster, massive Perseus cluster. And it showed that we could actually achieve the performance very much. And seeing, for example, in the Perseus cluster image, where you see the Perseus, that it's a cluster of about 1,000 galaxies. But in the background, we could see 100,000 galaxies.
So that are invisible to...
Which are, most of them are invisible.
Wow.
And instead, they are visible. And Euclid has this capability of having such a large field and such a definition that it can see everything very well defined, which is nearby and far away. Let's say we have this way of... really, and if you think that was 70 minutes of observation, if I remember well, 70 minutes, we have these 100,000 galaxies. And some of them are from 10 billion years away, 10 billion light years away, and the light comes from 10 billion years ago. So the earlier galaxies. And let's say to see that in one picture, and you say, now we are going to make 40,000 of those. So this is really something.
That's something. So any insights already for the main question, where all the dark places are and what they're made of?
Let's say the point, probably the less communication-friendly aspect of Euclid is that, as I said before, it's a statistical mission. So you really need to map a lot before you can really say something concerning the cosmology. Concerning distribution of dark matter, you can still do it even when you haven't mapped the full, because the dark matter is supposed to be around galaxies, it's supposed to be in certain areas. We will see where it is, but you can still have a local investigation, let's say more local investigation. Instead, dark energy, if it is true that what people think is actually a property of vacuum, a property of space itself, and you can only prove it to the required accuracy only if you really observe a big part of the universe, not only if you observe a small part. Otherwise, you don't see that effect. Or even more, if it is an aspect of gravity that is not really behaving like general relativity of Einstein predicted, that could also give, let's say we have probes also to measure how much deviation from gravity is, how much dark energy could explain that or not. So all these things, unfortunately, you will have to have a big share of the universe. So then I would say our mission is 6 years. I think nothing really a little bit sensible can be said before, let's say, 1/3 of that, 2 years or something.
So if you had a wish, what would you want the outcome to be of that mission?
But of course, the very sexy outcome would be that the cosmological model is not really the one that we think. Let's say the standard model we have, also the Lambda CDM is called. And let's say one could say, no, dark energy is just mimicked by a failure of gravity, a failure of general relativity to describe gravity. That could be a very sexy discovery. But honestly, I think everything will be good, and I just want to see what it is. So then, more than speculating on what it could be. And another thing that is also very important from Euclid is that, apart from the cosmological results, which are per se incredibly important, but there are a lot of what we call legacy science, let's say, because we will be making so much observations of extragalactic sky that in every field of astronomy there will be a benefit. I'm pretty sure it will be a bonanza of data from this mission that everyone will use. I was talking recently to one of the scientist of the science team, of Euclid science team, who is looking at ultra cool stars, planets like Jupiter, you know, that just in the border to become a star or not. And he could see many signs of that in some of the pictures we had recently. Just looking at this, but look at that, and here, this, I'm pretty sure this is an area where this planet, let's say, not around the star are going. I mean, these are subject nothing to do with cosmology, absolutely, but it's so many of those things will be really made available to the full science community, who will be making discoveries in all areas.
Do you have the feeling that we're on the cusp of something new when it comes to the standard model? Because, I mean, like the CERN people, the particle physics people are looking for it. Now, a couple of days ago, I'm sure you have heard of this paper by Johann Oppenheim, who claims to have a solution to the unification of general relativity and quantum mechanics. And this is being reviewed at the moment as we speak. But do you think that we're on the cusp of a new era in science to finally, after the 100 past years of relativity and understanding of how our universe works and not works, because 95% is still unknown, that we are venturing into something new? Or would that be non-scientific to ask such a question?
No, I think it's a good question to ask. It's also something that I'm asking myself. First, I'm not competent enough to really be able to, let's say, to have a global overview about the progress in the standard model and, let's say, the unification theories, etc. I have been following that, of course, a little bit in all my life because it's a fascinating aspect. But let's say for my job, we are not really not interested, but we are not really involved in looking at what the theoretical explanation could be, the theoretical model could be, but we are busy in providing real data. Mm-hmm. And to me, this is what fascinates me, because we have a lot of theories. Now you mentioned one, but let's say we have, there is a lot of theoretical speculations to unify quantum mechanics with general relativity and to give explanation to what we cannot explain, like this. And typically what one recur to is to, find the more, multiple dimensional theories like string theory, brane theory, etc., or other mathematical sophistication to be able to describe mathematically the reality. But in the end, then it will have to apply to something that we observe. Mm. Because if we cannot observe it, then it is not scientific, as you said. So then let's say, if you cannot prove, if your theory cannot say, let's say, you cannot describe an experiment that can falsify that comes from your countryman, philosopher, and that you cannot say anything. Let's say it's not even science. So what I'm really proud of what we are doing is that instead we are observing things and we are putting them on the table, and you have to observe them with the enough accuracy to be able then to make sure that the theory can be constructed or not. Because, of course, just observing without enough precision, you cannot constrain any theory. But what Euclid does is really observing with enough precision to be able to constrain theories.
At the end of our podcast, because you need to run to a Euclid meeting now, so let's be super quick. Maybe an unusual question. In case you're traveling to a distant place in the near future, someone calls you and says, Giuseppe, do you want to come along to go to Mars or whatever? It's a long journey. It's going to be very long and boring. What tune, what piece of music would you want to bring on your journey? Because it's going to be very boring. Which one tune? Because we have, which music, which song would you want to bring? Because we have a playlist on Spotify. It's called the Playlist for the Aspiring Space Traveler.
I see.
And which music would you not want to miss on that journey?
I'm a fan of the music of the 70s. That is my music. I was just really a fan of prog rock of the 70s.
Me too. Yeah. So which one will it be?
I never really thought. I mean, I have so many that I like. I am fascinated by White Rabbit of Jefferson Airplane, for example.
Good. So be it. It's not taken, so let's add that to the playlist. And the last question, this show is called Space Café Podcast. It's a coffee place for Italians, especially interesting. Why don't you now share an espresso for the mind with me, with the audiences, to energize our minds with some piece of inspiration? And you can pick whatever kind of topic you want to pick. What could be a shot of inspiration you think could be of relevance to our audiences?
You ask extremely difficult questions. But what I have a scientific formation. I work in science, and I believe that if we could be humbly working with a scientific method, with a scientific way of progressing, making progress we have in science, society would work better. Say, I don't like populism. I don't like all this type of promises which are without fundamental foundation. So if we could really stick to the reality and to the scientific reality, and in a humble way, I think as a society we could actually face the difficulties we have and the challenges that understandably we all have in a better way.
Giuseppe Racca, thank you so much for taking the time.
Thanks to you.
And that, my friends, brings us to the end of yet another episode of the Space Café Podcast. As we journey through the stars and delve into the mysteries of the universe, your companionship makes this adventure all the more extraordinary. If today's episode sparked new thoughts, stirred your curiosity, or simply gave you a moment of awe, we'd love to hear from you. So, take a moment, if you have a moment, to rate us and leave a comment wherever you listen to your podcasts. Share your thoughts or questions, and let's keep the conversation going. Remember, in the vast expanse of space, it's our shared human experience and curiosity that brings us closer. Until next time, keep looking up and let the wonders of the universe inspire your days and nights. This is Markus signing off from the Space Café Podcast. Stay curious, stay inspired, and most importantly, stay connected. Bye-bye.